Hi guys, let's have a review of circular functions. A bit of an introductory melting pot into what you should know about circular functions, but we're just going to make sure you know it before we continue on down the road of circular functions any further. So the first thing we should deal with here is radian measure. Okay, radian measure. What is a radian? Well, a radian, guys, in case you don't know, is basically that angle for which, if you have a circle of radius r, then the arc length subtended by that particular angle is also r, okay? That is 1 radian, okay? It subtends exactly the same arc length as the radius itself of the circle. That's 1 radian. Well, that's a pretty exciting definition. I heard you sigh. Don't worry. Don't worry, it'll get more interesting. So that's how it goes, and what can we do with it? Well, now we can convert between radians and degrees, okay? So how many radians are there in a full circle? I heard you ask. Well, let's figure it out. If you've got 2 pi r in the full perimeter of the circle and r in the arc length denoted by 1 radian, if we divide that full perimeter by r, we'd get how many radians would fit into one full perimeter, wouldn't we? Yes, see this r here, we're going to divide that into 2 pi r, which is all of that, right? To work out how many radians we can fit into a full circle, yeah? So that's going to be, we say that we know that there's basically 2 pi r over r, which gets us 2 pi radians in a circle. 2 pi radians in a circle, that's the magic number. So now let's do some converting now. We've got 360 degrees is 2 pi radians. Notice the little superscript C here for radian measure. Therefore, 1 degree would be, dividing both sides by 360, we get pi over 80. That's radians. Therefore, if we had x degrees multiplying both sides by x, this means we'll have this number of radians. So this is the formula for converting x degrees into the equivalent number of radians. We multiply the degrees by pi over 180, okay? Yes, that's what you do. Now let's attack it from the other angle now. We've got here, okay, 2 pi radians is 360 degrees, and therefore 1 radian dividing both sides by 2 pi would be 180 over pi, and therefore x radians, right, would be 180 over pi times x in degrees. So that's how to convert radians to degrees. You multiply by 180 over pi, right? That's how you do it. Now, do you get that? That's the formula that you've got to use to convert, okay, between degrees and radians. It's either pi over 180 or it's 180 over pi, apple of my eye, and you know why, because we have to do it. And it's very necessary to understand all this circular function stuff. So what do you need to know? Well, we need to know some common angles in degrees and radians. Here they come. That's the positive direction of an angle. This is the positive direction of the x-axis. This line here is 0, defined as 0 degrees. If we sweep around this way, we get positive angles. If we sweep around the other way, we get negative angles, okay? Okay, 180 degrees is pi. That's where I start. That's where I always start. 180 degrees, pi radians. 360 degrees, 2 pi radians. Did you know that? Well, you've got to know it, so you better learn it, okay? 90 degrees, on the other hand, that's half of 180, so that's got to be pi on 2 radians, yes? And then, oh yes, 270 degrees, that's, what's that? That's basically 3 times this one, 3 times 90, so it'll be 3 pi on 2. Yes, now let's go back into quadrant 1 now. 45 degrees, okay, that's, what's that? That's half of 90. 90 in and of itself is pi on 2. That's got to be half of that, so that gets us pi on 4. Okay, so far so good? Good. Now we better do 60 degrees. Now 60 degrees is a third of 180, isn't it? So that means it's got to be pi on 3. Yes, very good. Now, last but not least, 30 degrees. Well, 30 degrees is half of 60. If 60 is already pi on 3, then it's got to be half of that, which would be pi on 6. Yeah, happy? Alright, now look at this horrendous drawing here. This is a very, very quick recap of the symmetry properties of trigonometric functions. Well guys, it all starts here in quadrant 1, right? And if you had an angle A degrees here, or alternatively it might be B radian, but we'll just call it A degrees for now. If we had an angle A degrees, well, it has a certain value of its sine, its cos, and its tan. Yes, and in a unit circle, which this is supposed to be denoting, where this radius here is 1, and this black line here, that's like a hinge on the origin. That black line there is free to swivel around here like that, okay? Right? Swivel around like that, so the angle could change. So that basically in this triangle here, we could say that if it was a unit circle, sine of A degrees would be this red height here, or the y coordinate over 1, just the y coordinate. Cos of A degrees would be the blue line here, or the x coordinate over 1, or just the x coordinate, right? And tan, of course, would be the red line over the blue line, which is the opposite over the adjacent. Now, the symmetry properties tells you that in every other quadrant, this one, quadrant 2, this one, quadrant 3, and this one, quadrant 4, there exists an angle which has exactly the same values of its sine, cos, and tan as this angle does here, this A degrees in quadrant 1. They might be positive or they might be negative, but the numerical value of sine and cos and tan will be exactly the same as they are for this angle A degrees. And the key to this, guys, the key to this is that in these other quadrants, where we're sort of outside the realm of a normal right angle triangle here in terms of the angle which we're defining, for example, in this situation here, that black line there has swept through what angle from the positive direction of the x-axis? Watch my little green hand. It's going round to there. That's the angle that they're sweeping out, right? So if you could imagine this might be, I don't know, let's say A was 30 degrees, for example. Yeah. Therefore, now what you would get, guys, is what I want you to understand is that the angle in this quadrant that has the same sine as 30 degrees would be, if you think about in this quadrant how far we are away from the horizontal axis, right? Now this angle in here, for this congruent triangle, this is exactly the same congruent triangle, same dimensions, same angle, same everything as this triangle here in quadrant 1. And while we're at it, this one and this one are also identical in their shape and the angles. Everything's the same. So they're congruent. They're identical in all respects. Now going back to this quadrant here, if we think about what distance are we, or what angular distance are we from the horizontal line here, the horizontal? Well, we're A degrees short, actually, of 180 degrees, aren't we? Okay, so if you think about that, if you think about any angle that's in this quadrant, or this quadrant here, or even this quadrant here, and you think about where we are away from the horizontal axis, then you get the angle that this is either shortfall by or in excess of the horizontal, and that angle is the key to the angle over here, for which this particular angle in quadrant 2 or 3 or 4 has the same sine or cos or tan of in quadrant 1. For example, let's just say this, as I was saying, this is 30 degrees. Well, if that was 30 degrees, then the angle in quadrant 2 that has the same sine is the angle for which this is 30 degrees. Here, this is 30 degrees. Because for that triangle, it has exactly the same red line, exactly the same blue line. And remember that in quadrant 2, 3, and 4, we just take the y-coordinate as being sine, and we take the x-coordinate as being cos. Okay? That's what we do. Now, moving right along, if that was 30 degrees there, therefore this angle here from the positive direction of the x-axis would be 120. no, wouldn't it be 150? 150 degrees, so that I'm saying to you that the sine of 150 degrees is 30 degrees short of 180. 30 degrees, okay? So therefore the sine of 150 will be the same as the sine of 30, right? Because the triangles are identical, and this angle here is 30. That's what I'm saying. Now, it happens that sine is positive in this quadrant because that y coordinate is positive in this quadrant. Now, in this quadrant here, we could say, okay, well, if we were dealing with 210 degrees, then this angle here would be 30 degrees. That angle there would be 30 degrees. Therefore, 210 degrees has the same sine as 30 degrees, except in this case that this is a negative y. That's a negative y in that quadrant. That's a positive y. So therefore, I can say to you that sine of 210 degrees is 180 plus 30. It's 30 degrees removed from the horizontal axis. Therefore, sine of 210 degrees is minus sine 30, right? Similarly, in this quadrant here, I could say to you that sine, if this angle here was 30, then this would be 360 less 30 degrees, right? That's the 30, we're 30 degrees removed from the horizontal axis. Therefore, sine of 330 degrees would be the same as minus sine 30, because it's a minus. This is a minus. This is a negative y coordinate. That's how it goes, guys. That's how you do it, okay? That's the symmetry that we use when we're considering quadrant 2, 3 and 4 angles, and we relate them back to a quadrant 1 angle. We consider how far the angle is removed from the horizontal. And that angle, however far it is removed, that particular angle is the same angle as we're looking for in quadrant 1. That's what we're talking about. Hope I spat that out reasonably clearly. Now, if you got confused by that, this is going to really finish you off, I'm telling you. Because in complementary angle symmetry, in relating to quadrant 2, 3 and 4, and even we can do this in quadrant 1, we consider, when relating back to this particular triangle situation here, we consider how far in whatever scenario we've got we are removed from not the horizontal axis but the vertical axis. Now the best way for me to explain to you is this, is to pick an angle. Say for example we had a 30 degree angle in there, in our original unmessed with triangle here, right? And we've got a horizontal side here and we've got a vertical side there. Now, say that was 30. Now, say for example I wanted to do the sine of 120, right? So therefore, now let's have a look at this. 120, as it turns out, would be, say, this angle here, as we're sweeping around from the positive direction of the x-axis. That'll be 120. But this angle in here, just past the vertical, the y-axis, from there to there, that's going to be 30, right? That's going to be 30. So therefore, we can consider 120 degrees to be 90 plus 30. 30 degrees removed from the vertical axis, right? Now, therefore, sine of 120 being 90 plus 30 would be this vertical y-coordinate over 1, yes? Now, if you relate that back to our unmessed with triangle, this is our original triangle here, that vertical line is equivalent, identical to in length, to this horizontal line here, right? So if sine of 120 is sine of 90 plus 30 and it's equal to this blue line over 1, that's basically going to be the same ratio as this one over this one, which is going to be cos of 30. You see that? See, so if you consider this sine of 90 plus 30 is the same as cos of 30. Now, by the way, this triangle here is absolutely congruent to this triangle here, identical in all respects, except that it's just tipped up on its end. See, because if that's 30 there, then in here you've also got 30 because of these vertical parallel lines here, the blue line and the y-axis. Therefore, if that's 30, that's got to be 60, that's got to be 90, and you've got 30, 60, 90 here, and if the black lines are the same length, then they're congruent triangles. That's how it works. Now, that's what you do. In complementary angle symmetry, you always consider any angle that you're dealing with, if you want to relate it back to this quadrant 1 conventional angle, you always consider how far it is removed away from the vertical axis. And that's basically how you work back to its equivalent sine or cos or tan of an angle in this little triangle here. I'll give you another example. What if we said cos of 60, right? Cos of 60, doing it as a complementary angle thingy, we'd say, well, 60 is quadrant 1, so that's got to be 90 minus 30. So cos of 90 minus 30, which is this 60 degrees, right, is going to be cos of 90 minus 30 is going to be this one here, adjacent, over hypotenuse, yes, right, so it's just going to be this length or this x coordinate, which if you relate it back to our conventional triangle is going to be the same as this line here, this line over 1. So cos of 90 minus 30, which is the same as cos 60, but we consider it to be 90 minus 30. Cos of 90 minus 30 is going to be the same as sine 30. See the 30 and the 30. 90 minus 30 gets you sine of 30. Okay, so that's how you do it. And how far it is removed from the y-axis, that angle is the size of the angle that you'll get back in this triangle here. So it works out. Now here's the quick and dirty way for you. It works out that if you're dealing with cos of a complementary angle thingy, such as cos of 90 plus 30, the answer is going to be sine. If you're dealing with sine of 90 plus 30, the answer is going to be cos. So if you're dealing with a cos complementary angle situation, the answer is going to be sine of this one back in this triangle. If you're dealing with sine of a complementary angle situation, it's going to be cos, right? Now, the way you work out whether it's going to be positive or negative is you'd say, all right, say if we did cos of 90 plus 30, well, you know that cos in this quadrant, and this quadrant here is negative, so the answer is going to be negative, because only sine is positive in this quadrant. So cos of 120, which would be 90 plus 30, would be the same as minus sine 30. That's how it works. That's how it works. And incidentally, tan gets you 1 over tan. So tan of 90 plus 30, tan of 90 plus 30 will get you minus 1 over tan 30. That's what happens. With tan, you get the reciprocal. You're thoroughly confused. Oh, well, I tried, didn't I? You better just think about it and go over it again. So I'll give you another example, a quick and dirty method here. What if I said to you, all right, what about the cos of 270 minus 30, right? That'd be this one. There. So 270 minus 30 would actually be 240 degrees. But if we consider it to be 270 minus 30 cos of, then cos is negative in this quadrant, so it's going to be minus sine 30. Right? That's how you do it. Now, I better not start rabbiting on because that'll take up too much time. But that's basically how it all works. You get that? You better watch the video again. Here's some practice for you. It's called complementary angle symmetry because when you do quadrant 1 angles, when quadrant 1 angles are considered, we always express the answers in terms of the complementary angle. That's what it is. E.g., cos of 70 is sine of 20. Okay? And tan of 65 is 1 over tan 25. That's how it works. Practicing, here we go. Sine of 120. Now, if we went, that's quadrant 2. If we went conventional, conventional is where you're considering your distance away from the horizontal axis. So you'd say, well, 120, that's quadrant 2, that's 60 degrees short of 180, which is the horizontal. So that's basically sine of 180 minus 60, which will be the same as sine 60, because positive in quadrant 2. Yeah, that's how you do conventional. Now let's do unconventional now. Oh yes, that's root 3 over 2. Complementary, you'd say, well, 120 is 90. See, relative to the vertical axis. 90 plus 30, which will be basically the same as cos. Remember, if you've got sine of a complementary, the answer will be cos. and it's cos of 30 because this is the angle. This is the critical angle that we're trying to find, right? There, cos of 30, which is also because sine is positive in quadrant 2, it's also going to be root 3 over 2. Righto, cos of 70, quadrant 1. Conventional, well, it's just cos 70. Okay, that's just cos 70, whatever cos 70 is. Complementary, you'd say, okay, that's going to be cos of 90 minus. Wait a minute. Yeah, I just fixed that up. It'd be cos of 90 minus 20, and there you think of it as a 90 minus because it's quadrant 1. It's 20 degrees short of 90, so it's 90 minus 20 relative to the vertical axis, remember. That's going to be sine of 20. And, you know, for your information, cos of 70 is the same as sine of 20. Okay, so that's how that works. What about sine of 210? Well, conventional, that's quadrant 3, isn't it? So with conventional, you'd say, oh, well, that's 180 plus 30. So that's going to be the sine of 210. Sine is negative in quadrant 3, so that would be the same as minus sine 30, which would be minus a half. Yeah. If you went complementary, you'd say, well, I've got to do that's in quadrant 3, therefore it's got to be a 270 minus to get me into quadrant 3 relative to the vertical axis, which adjoins quadrant 3. So 210 is going to be 270 minus 60. Now, if you're doing sine, the answer is going to be cos, and we are doing sine. Sine is negative in that quadrant, so it's going to be minus cos 60. Minus cos 60, which is minus a half, which is what we got over there. Same thing. See, you get it? Yes, you do. I know you do now. You're getting it now. Okay, cos of, what's that? 280, is it? Cos of 280. All right, let's go for that. That's quadrant 4, isn't it? It's 10 degrees past 270, isn't it? So conventional, though, you'd say, well, that's how far are we removed from the horizontal, which is the 360 degree mark. So that would be, what would that be, 80 degrees short? So it's 360 minus 80, which would be the same as plus cos 80 degrees, right? That's what you do with conventional, whatever cos of 80 degrees is, I don't know. But we'll just leave it like that. Complementary wise, you'd say, well, no, we've got to think of this relative to the vertical axis. Yeah, so that's going to be the cos of 270 plus 10, which will be cos is positive in quadrant 4, so it's going to be plus sine 10 degrees. Yeah, cos is positive in quadrant 4. Do you get me? Oh, here's another one. Tan of 70. Okay, now this is a tan one. Now remember I said if you go complementary with tan, you get 1 over. So I won't preempt that, but we'll do it conventionally first. Quadrant 1, well, that's just going to be tan of 70, isn't it? Yes. Now, conventional, though, you'd say, well, I've got to do this relative to the vertical axis, so therefore the vertical bit of the vertical axis which exists in quadrant 1 is the 90 degree mark, the positive bit of the y-axis. So therefore, what are we saying? We're saying that's the tan of 90 minus 20, and that'll get us back to 1 over tan 20. 1 over, when you do it complementary. Tan to get 1 over tan of the complementary angle, if you like. What's this one? Tan of 1 over 20. Okay, what's that going to be? Okay, that's all right. Conventional, quadrant 2. Yeah, quadrant 2. Conventional is going to get us, that's 60 degrees short of 180. So it's 180 minus 60, which in quadrant 2, because tan is negative in quadrant 2, will be minus tan 60. Minus tan 60, what's tan of 60? It's root 3, isn't it? Yeah, well, I didn't write it down, but it is. So that would be minus root 3. Now, complementary, though, tan of 120 would be tan of 90 plus 30, which would be minus 1 over tan 30. Minus 1 over tan 30, because tan is negative in quadrant 2. Yes, we got that. Now, here's the quick rules. The quick rules, I state in my class the quick and dirty rules, but they're just the quick rules for complementary angle representation. Here we go. Represent the angle as 90 minus theta quadrant 1, 90 plus theta quadrant 2, 270 minus theta quadrant 3, 270 plus theta quadrant 4. Use the cast diagram to determine the sign, the SIGN, positive or negative of the answer, e.g. sine of 270 plus 10, quadrant 4, therefore sine would be negative. You'd get a negative answer in quadrant 4, yeah? So, for sine of a complementary represented angle, relative to the vertical axis, For sine of it, you're going to get cos for the answer. For cos of it, you're going to get sine for the answer. For tan of it, you're going to get 1 over tan for the answer. And the angle in the answer will be the theta bit, this one up here, whatever that theta bit is there, right? Whatever that theta bit is in there. Okay, e.g. sine of 280, quadrant 4, that's basically sine is, you say, okay, sine is negative in quadrant 4, and 280 is 270 plus 10, so it's going to be negative cos 10. Okay, either e.g. cos of 120, that's going to get us, what's that going to get us? Quadrant 2. Cos is negative in quadrant 2, so the answer is going to be, that's 90 plus 30, so it's, the answer is going to be minus sine 30, which would be minus a half. Yes? Alright, that was pretty painful, wasn't it? Well, hope you get it. Last but not least, we're going to do the symmetry of negative angles. Now, this is actually something we really need to take notice of, although we're probably all exhausted after all that stuff I've just been dealing with. But just hang on for another couple of minutes and you'll have this right. Now you know that if I go around this away, that's the positive direction, right? From the positive direction of the x-axis in an anti-clockwise direction, that's a positive angle. If I go around this away, however, sweeping around this way from the positive direction of the x-axis, I'm going clockwise and I'm getting a negative angle. So, okay, we've got to see, if we have an angle in here, we call it theta, for example. This one's showing 21.26, but we'll just call it theta. Sine of theta is this positive y coordinate, right? Yes, but sine of negative theta, okay, identical triangle but in the negative, right, will be this, will be a negative y coordinate. So you see, look, in this case that I've got shown in this diagram, sine of that angle was 0.36, it seems. Yeah, because the y is 0.36, right? But this one here is minus 0.36, so therefore sine of minus a is minus 0.36, which is minus sine a. So what am I saying? I'm saying sine of minus a is minus sine a, relating it back to this situation here as our reference, right? And similarly cos, now cos, okay, cos of this angle would be this blue line here, over 1, because it's a unit circle, okay, but so cos of, say, theta, in this case would be the blue line, but cos of minus theta would also be the blue line, okay, they're both positive, so therefore, what am I saying? I'm saying cos, if you call it a, for example, not theta but a, cos of minus a would be minus, oh no, it wouldn't be, it would be plus. Cos of minus a is plus cos of a. It's the same sign as it, right? Now the strange thing, ladies and gentlemen, is that it doesn't matter how far you go back into the negative realm. You can go around thousands and thousands and thousands of degrees, it doesn't matter, any number of revolutions, you'll still get that same relationship will apply. In other words, okay, we'll say it again, sine of minus a is minus sine a, and cos of minus a is just cos of a. And tan, while we're at it, tan behaves the same as sine. Okay, so tan of minus a will be minus tan a. And if you care to prove that to yourself, it'll work, because tan is the red over the blue. Okay, so for a degrees here, red over blue, they're both positive, will get you a positive answer, but tan of minus a will get you a negative over a positive, which is negative. So therefore tan of minus a is minus tan a. Oh my goodness. So there we go. Summarise. Let's summarise and get out of here. So therefore sine of minus theta is minus sine theta, or sine of minus a is minus sine a. Cos of minus theta, or cos of minus a, is plus cos of theta, or plus cos of a. And tan of minus theta, or tan of minus a, is minus tan theta, or minus tan a. Today, hooray, we're out of here. Now, if you didn't get that, please go back and have another look. I hope I've done it justice. It can be very difficult to explain this stuff, but I hope I did a reasonable job, and I hope you got something out of it. So go and do some practice. If you get, the only way to get this really is to do practice and to ask if you're stuck. Okay, all the best with it, and we'll see you next time. Bye.